Swayam Prabha. Digital India. Educated India.
We have the topic Buoyancy being presented by Darbari Lal Foundation Public School and Ramjas International School. We will start with Team A of Darbari Lal Foundation, which comprises of Avni Adhikari of grade 10 and Rohan Ranjan of grade 10. Let's welcome them.
Hey there, fellow adventurers, behold your breath. For I, Captain Avni Aquaventure and Captain Rohan Ripple Seeker are going to take you on a deep sea dive on the Buoyancy expedition in our latest Marine Marvel Quest episode 325. Hey, hello everyone. Our mission for today is to understand how aquatic animals use buoyancy to explore vast ocean depths. Are you ready to dive into this experiment?
To kick things off, let's dive into our miniature model of the marine ocean. Today, we are embarking on an exciting adventure into the world of marine biology and the role of physics in it.
Now gather round, explorers, as you see the toy fish, aquatic plants and other objects. Those represent marine life. As you observe, some objects sink, rather others float.
A quick treasure hunt. Buoyancy is the upward force exerted by a fluid such as the water or air that opposes the weight of an object placed in the fluid.
This force allows the objects to float or be suspended in the water. If the object is less denser than the fluid it displaces, it will float, or if it is more denser, it will sink.
And now the fun part. Observe carefully. As you can see, as Avni blows the balloon, it inflates the balloon inside a tiny model fish that mimics the real underwater creatures' swim bladders or the buoyancy control mechanisms.
A swim bladder is like an expandable sac filled with oxygen from the water extracted by the gills. This allows the fish to control its buoyancy. If the bladder is completely inflated, it has maximum volume and hence the least density. As you all might know, density's formula is mass upon volume, and hence the fish is pushed upwards. Whereas it's vice versa, when the volume is very minimum, hence the fish has the highest density and it sinks to the ocean floor.
Talking about fish biology often raises questions about how can even larger fish prefer to stay on the surface while the smaller fish thrive in the extreme depths.
The answer lies in the various adaptations these organisms have, such as including body size, buoyancy control mechanisms, and physiological adaptations.
Smaller fishes having a higher surface area to volume ratio experience less buoyant force, making it easier for them to navigate at deeper depths.
In contrast, larger fish like dolphins rely on dynamic swimming techniques due to their greater mass. Hence, they have to periodically surface themselves up as they don't have gills to breathe. And this shows a delicate balance between adaptation and survival in aquatic environments.
Deep sea dwellers, such as the blobfish, have unique physiological adaptations like low density flesh that helps them to cope with extreme pressures as they inhabit the seafloor at around 600 to 1200 meters of depth.
Additionally, behavioral adaptations play a crucial role, with certain species actively regulating buoyancy to navigate diverse depth zones. For example, certain species may swim upwards to shallower depths during the day, whereas the other species may swim to and descend to deeper waters during the night, where temperature and pressure conditions may vary. But while discussing marine life, Rohan, I have a question for you. Why do we have two distinct pots here then?
Density is a key factor creating distinctions between river and ocean water. River water is less dense than the ocean water due to several factors such as dissolved minerals, sediments and organic matter. Ocean water having a higher salinity has higher average density.
Oh yes, and the same kind of concept goes for the aquatic plants as well. They have several adaptations to stay afloat and thrive in waters.
As we are talking about density, let's talk about the two non-mixing oceans as we think it as of illusion. At the meeting point of the Pacific Atlantic Ocean, near the Atlantic convergence, cool, dense, nutrient-rich waters from the southern oceans meet the warm, less dense water from other oceans. This creates layers that prevents immediate mixing.
As we wrap up our underwater expedition, I hope this hands-on adventure sparks your curiosity about the incredible adaptations these marine organisms have to swim and navigate their underwater homes.
A massive thanks to our fellow explorers for joining us in this buoyancy expedition. Until our next adventure, keep exploring, stay curious, and the currents be ever in your favor.
Goodbye.
Now we have Nilakshi Kumari of Grade 10 and Nikunj Gupta of Grade 10 representing Team B. Let's welcome them.
Ever wondered how different objects float or sink in fluids? Isn't it astonishing how such large marine objects such as ships and cruises float in the ocean, whereas an object as small as a coin sinks? Let's explore the science behind it.
Welcome fellow scientists to the realm of buoyancy. Today I, Nikunj, along with my fellow explorer Nilakshi, are here to demonstrate the science behind buoyancy.
Get ready to first-hand experience the magic of experimentation as we uncover the secrets behind buoyancy. A long time ago, Archimedes had used this principle to prove that the crown of King Hermod II was not made of pure gold.
He did this by taking two portions of gold and silver, each equal in mass to of the crown, and put them in a beaker which was filled to the brim with water. He then recorded the amount of water displaced by the crown and both the portions. His observation stated that the crown displaced more water than the portion of the gold, which states that the crown was not made of pure gold and there was some silver added to it.
Our motive is to give a clearer view of how buoyancy and density work in liquids. We'll observe this through an experiment, so let's delve into it. So first of all, we'll pour some honey into the beaker. Next up, we have water. And last but not the least, oil. As you can see, none of the three liquids have mixed with each other.
The tendency of liquids of different densities to not mix is primarily due to the principle of buoyancy. When you have two liquids of different densities, the denser liquid tends to sink below the less dense one. This is a result of the buoyant force acting on the liquids.
The buoyant force is an upward force exerted by a fluid, liquid or gas on an object immersed in it. If the object is less dense than the fluid, it experiences a net upward force causing it to float. However, if it is denser than the fluid, it experiences a net downward force causing it to sink. In this case of the three liquids, honey with the highest density has sunk to the bottom, whereas oil with the least density is floating on the top.
We have calculated the densities of these liquids by first measuring the weight of a sphere in air and then in the specific liquid. The weight lost becomes the weight of the displaced fluid, and by measuring its volume and putting it in the formula m by v equals density, we have found out the density of these specific fluids.
Now we'll observe how different objects react to these liquids. First up, we have a nut. As you can see, it has sunk to the bottom of the beaker. Next up is a raisin. The raisin is floating on honey but has sunk in water. Next up, a Lego piece. As you can see, it's floating on water but it's sunk in oil. Lastly, a sponge, which is floating on the oil.
Moving on to objects that sink in oil but float on water typically have more density than that of oil but less than that of water. The same principle applies for the objects that float on honey but sink in water. The raisin, when dropped into the glass, experienced a buoyant force directed upward, but this force was not enough to counteract the gravitational force pulling the object downward. As a result, it sinks in water.
However, when the same object is taken as an example for honey, which is denser than water, the buoyant force experienced by the object will also be greater. The raisin, when dropped into the glass, when dropped into the beaker, experiences a greater buoyant force, causing it to float on honey even though it sinks in water. In summary, an object's ability to float or sink depends on its density compared to the density of the liquid it is placed in. The specific densities of honey, oil and water also play a crucial role in determining the buoyancies of these objects.
Moving on to the real-life applications for the above principle, some notable examples include the functioning of hot air balloons and submarines. A hot air balloon rises up in air due to the principle of buoyancy. When the air inside the hot air balloon is heated by the burner, it becomes less dense than the surrounding air. Since objects in a fluid like air are buoyed upwards with a force that is equal to the weight of the displaced fluid, the less dense hotter air causes the hot air balloon to rise as it displaces a greater weight of the cooler, denser air. This creates a lift which causes the balloon to float upward.
As you can see, the factors affecting buoyancy in hot air balloons include temperature variations, volume and weight of the balloon, the surrounding atmospheric conditions, altitude and volume of the air displaced. Moving on to the second application, submarines. A submarine stays afloat primarily through the use of ballast tanks and buoyancy control systems. By adjusting the amount of water in these tanks, a submarine can either float or sink in liquids. When it needs to surface, it pumps air into these ballast tanks, displacing water and increasing buoyancy. And when it needs to dive, it fills air into the same tanks to increase the density, causing it to sink.
Even in the legendary tale of Ramayana, Lord Ram along with his army of monkeys built an extraordinary bridge known as Ram Setu or the Adam's Bridge using some rocks with a unique composition that allowed them to have density less than that of oceanic water to allow them to stay afloat and complete the bridge.
With this, we would like to conclude our presentation. We hope you all enjoyed it. Thank you.
We have our first team present with us. Team A, Vanisha Shah from grade 10 and Sukhmanjeet Kaur from grade 10. Let's welcome them.
Greetings everyone. I am Vania Shah
And I am Sukhmanjeet.
and today we are going to be exploring the concepts of buoyancy together. Sukhman, do you feel any weight on your head?
Yes, of course, Vanya. It's heavy.
It's so funny that you feel even the slightest of weight on your head. But ever wondered that why we don't feel the weight of our brains on our head?
The average weight of a human brain is 1500 grams, but it is reduced to 50 grams due to buoyant force acting on it.
Buoyant force? What is that?
Let me explain you. Imagine yourself in a pool on a hot summer day and feeling as light as a feather as you float effortlessly on water surface. The sensation you experience with the water lifts you up and hold you there is the buoyant force. It is like a gentle invisible hand helping objects to float, just like the pool does for you.
Okay, so you mean that the buoyant force is a vertically upward force exerted on objects immersed in a fluid?
You're absolutely right.
Also, according to the Archimedes principle, it is equal to the weight of the fluid displaced by the object. The greater the fluid displaced, the more is the buoyant force. If the buoyant force is more than the object's weight, it floats. If it is less, it sinks. This principle explains why heavy ships can stay afloat on water and boats float on water.
Now think of buoyancy as nature's magical hug for objects in fluid. It is like a secret cheerleader beneath the surface, nudging things up and saying, "You got this, stay afloat." Just as a kite soars in the sky with wind support, buoyancy lends a helping hand to objects in fluid. It lifts them up and gives them the freedom to float and glide effortlessly.
Now, let's look at some applications of buoyancy in our very own body. The human brain encased within the protective cranium is a marvel of biological engineering. The cerebrospinal fluid, which is depicted by the blue color here, helps the brain maintain its structural integrity and functionality. Now, let us do an experiment.
Imagine this tomato as your brain.
Now, we'll pour some water here and let's assume that this water is the cerebrospinal fluid. As seen here, we can see that the tomato neither floats nor sinks. This represents neutral buoyancy. In a similar manner, our brain shows neutral buoyancy in the cerebrospinal fluid. Let's look at the other two types of buoyancy, that is positive buoyancy and negative buoyancy.
For that, we'll take some water in a container. Now here we have two objects, a stone and a feather. What about this feather? What do you think? Will it float or sink?
I think that this should float.
Let's see. Yes, you're right. It floats.
And it shows positive buoyancy.
Now let's try with other object. This is a stone. What do you think about this?
This should probably sink.
Let's see. Oh, you're right again.
It sinks because it represents negative buoyancy. Buoyancy also plays a crucial role in the development of a fetus floating in amniotic fluid. The amniotic fluid provides buoyant support to the developing baby to grow with reduced gravitational constraints. This buoyancy also helps in the development of muscle, bone, and overall mobility of the fetus as it experiences a gravity-neutral environment.
Ladies and gentlemen, now please pay attention because now we are moving on to the most exciting part of the day, that is exploring buoyancy with dancing raisins experiment. Our experiment delves into the fascinating realm of buoyancy, seeking to unravel its mysteries through hands-on exploration and observations. Our objective is to observe how buoyancy affects different objects in a liquid, specifically raisins in vinegar with baking soda. Materials required are a container, vinegar solution, some baking soda, and some raisins. First, we'll pour some vinegar into this beaker. Now, we'll add some baking soda into it. Now, we'll add a few raisins into it. We'll observe what happens to raisins over time.
We observe that as the carbon dioxide bubbles pop up, the raisins slowly start dancing and move.
I'll explain why. As the carbon dioxide gas bubbles attach themselves to the surface of raisins, they become less dense and hence the raisins rise up. When they come to the surface, the bubbles pop and the buoyancy, and then the raisins lose their buoyancy and sink back down. This cycle repeats and hence it is seeming that the raisins are seeming to dance.
Through this experiment, we came to know about buoyancy. So friends, remember that science is all about exploring and learning about the things around us. We hope that through our presentation, you came to know a little bit about buoyancy. Thank you.
Now we come to the last presentation by Team B, represented by Divyanshi Bhisht of Grade 10 and V. Sindhuja of Grade 10 as well. Let's welcome them.
Buoyancy, the art of rising even when the tide is against you. Good afternoon, everyone. Today I, Divyanshi, and my teammate Sindhuja are here to present some experiments on buoyancy.
Hey Divyanshi, have you ever wondered why some objects float while others sink in fluids?
Yeah, I've always found that interesting. Isn't it something to do with density and buoyancy?
Exactly. Let's demonstrate this via an experiment. I already have all the material that we need, which are a bowl filled with rice, a bowl of rice, a tennis ball, and a metal ball.
We're going to use this transparent container filled with rice. We'll bury a tennis ball into the rice. We're going to place that metal ball on top of the rice. Okay, we'll shake the container and observe what happens next.
Look at that. The tennis ball has risen up to the surface.
And the metal ball has sunk even deeper into the rice. It's like the tennis ball has its own force which is pushing it upwards.
Exactly. It is called as buoyancy. Buoyancy is a force that arises from the pressure exerted on an object by a fluid. It is also known as buoyant force.
So, you're saying that tennis ball floats over rice because it is less dense than rice, and the metal ball sinks even further because it is denser, right?
Exactly.
Now, why not show buoyancy in liquids?
But before that, let us understand what buoyancy actually is. In simple terms, buoyancy is the ability of any object to float, rise, or sink in liquids or fluids. By the way, have you heard about positive, negative, and neutral buoyancy?
Let me guess. Is it related to sinking, floating, and rising of objects in a fluid?
You are right. Positive buoyancy is a case where the object floats on the water due to its less density.
Oh, then negative buoyancy must be a case where an object having high density sinks into a fluid.
Exactly. And neutral buoyancy is a case where the average density of the object is equal to the density of the liquid in which it is immersed.
Moving further, let's demonstrate an experiment to show buoyancy in liquids. For this experiment, we'll be needing a glass, a metal piece, honey, oil,
grape, a plastic cap, watercolors, and a spoon. But before we start, let us understand the difference and the relation between density and buoyancy.
Buoyant force is directly proportional to the density of a liquid displaced. So, the greater the density of a liquid displaced, the greater will be the buoyant force.
Moving on, let's begin the experiment by adding water. As we all know, water has a density of 1 gram per centimeter cube. Then we will add honey. Honey has a density of 1.4 grams per centimeter cube. Then we will use watercolors to separate the layers of water, honey and oil, which we will add soon.
When oil is added to the glass, it floats over the layer of water. Why does this happen? This happens because different liquids separate into different layers because of having different densities. And this is the main reason as to why these liquids don't mix together and float over each other.
As you can see, honey having the highest density settles at the bottom of the glass, and water having less density as compared to that of honey floats on the layer of honey, and oil having the least density among all the 3 liquids that have been taken floats on the layer of water. Now, let us add a metal piece to the glass. Metal piece having the highest density sinks to the layers of oil, water and honey settling at the bottom of the glass. Now, let us add a grape to it. The grape, having less density as compared to that of a metal piece, sinks to the layers of oil and water settling on top of honey.
When plastic cap is added to the glass, it slowly sinks right through the layer of oil and settles over water. This is because it is less dense than a grape. Now, when sponge is added to the glass, it floats over the layer of oil because sponge has lots of vacant spaces which allow the air to pass through, and this is also, it is less dense.
We conclude that density and buoyancy are interdependent. I hope you guys understood the concept of density and buoyancy. Thank you.
And now it's time for the judge's opinion.
And last but not the least, In the fifth topic, buoyancy, the winner is Ramjas International School, and participants are Divyanshi Bisht and V. Sindhuja.
And the runner-up is also Ramjas International School, and the participants are Vanya Shah and Sukhmanjeet Kaur. Congratulations to all the winners.